Okay, we're going to talk now how to change derivatives to polar coordinates. And I can tell you from experience, this is a very useful calculation that will probably be used in upper division science classes, because there are so many situations where cylindrical and spherical symmetry are useful to scientists. So the problem that I'll be considering is if z is a function of x and y, and for example, x equals r cosine theta and y equals r sine of theta, we're using polar coordinates. The problem is to find partial derivatives with respect to r and theta, and then we're also going to find the second partial derivative with respect to r and theta. So I would say this was hard. So I'll be going over this calculation in some detail. These, I would say, these just follow from the chain rule. And the chain rule, how would I do the chain rule in this case? I would, for the sake of simplicity, I would write z as just a function of x of r and y of r. So treat as a 1D function. So now apply ddr. So dz dr, it'll just be f sub x, x prime of r, x of r. I'm again using lazy notation, which is f sub x equals the partial derivative of f with respect to x, and x of r is the partial derivative of x with respect to r. I just like to save time because you can see this is going to kind of snowball into a sequence of terms. And f sub y, y sub r, and the way I like to remember this formula, just in case this is confusing, is you have cancellation with these x's and y's, and the r matches the left-hand side. So similarly, dz d theta, you could just treat this as a function of theta only, and just think about applying it in 1D senses, if this helps. If it's confusing, ignore what I'm saying here and just use the chain rule. And I like to think about it as cancellation. Okay, so dz d theta, so f sub x, there's going to be an f sub x, there's going to be an f sub y, and in order to have cancellation, we'll have x sub something and y sub something, and that something is precisely theta to match the left-hand side. Okay, so now let's actually compute some stuff. We need to compute the x, y stuff. So x of r, this will be r cosine theta derivative, so it's just cosine theta. So y sub r will be similarly sine theta. And x sub theta, this will be minus r sine theta, and y sub theta will just be r cosine theta because I'm differentiating in theta. So if you just plug these things in, we'll just get f sub x times cosine theta plus f sub y times sine of theta. If we plug this in, we'll just get f sub x times minus r cosine theta plus f sub y times r. Oh, I'm sorry, this is minus r sine theta. R sine theta, r cosine theta. And if you're like me, you will get kind of annoyed with writing cosine and sine. Again, you can tell I'm a very lazy person. So I'm gonna make this even more compact. Z sub r equals f sub x, and I'm just gonna copy and paste what I wrote over there. F sub x cosine theta. I'm gonna call this c plus f sub y times s. C equals cosine theta. S equals sine theta. So you can see I'm saving some time here by writing this, although it possibly could cause some confusion. So again, I'm going to copy paste this. So it's s of x times minus rs. Remember, sine theta is s, plus s of y times rc. So now we just need the hard part, d squared z, and we'll have the mixed derivatives. People call this the mixed derivative because you're mixing r and theta. So how do we do this thing? I would differentiate the simpler one. So I would differentiate the simpler expression. And that one is just zr, because there's no extra r, like when z theta. The extra r that I'm talking about is this one right here. Okay? So if I do that, I want to compute zr theta. That is this thing. That's a lazy notation for this derivative. What I'll do is I'll apply dd theta to z sub r, and that is this expression up here. So I'll plug that expression into dd theta. And so now you can see why my compact notation is kind of helpful, because you can see there's going to be a lot of terms. So here's where the complication comes from. dd theta applies both to f sub x and to cosine theta. So you have two terms, two types of terms. The first type is where you're just applying dd theta to f sub x. The second type is where you're applying dd theta to cosine theta. So I'm just going to split these two terms. So I will say the non-theta stuff. And then here I will call this the theta stuff. And you'll be adding these two things. Okay? So I'm just saying do this step by step. So for the non-theta stuff, I will put the c on the outside and apply the derivative of theta to f sub x. And similarly, the s will go on the outside, and I will apply the derivative of theta to f sub y. And for the theta stuff, I will now put f sub x on the outside and apply derivative of theta to c. And similarly, f sub y, I will apply the derivative of theta to s. And what am I doing? I'm just doing the product rule. Right? Because dd theta of f sub x c, surely this is just c dd theta f sub x plus f sub x dd theta of c. Okay? And so what I'm doing is I'm using the product rule to split this up into two types of terms to clarify what's going on. Okay, so let us now evaluate some stuff. So zr theta, to reiterate, I will have two types of terms. I will have c dd theta f sub x plus s dd theta f sub y. And then finally, down here, I'll have f of x times dd theta of c plus f sub y dd theta of s. Okay, so these ones are actually easy, right? Because the derivative of cosine is minus sine. Derivative of sine is just cosine. So that one's very simple. I would say these ones are the hard ones. So how you do this is you use the previous calculation and replace f with fx or fy, depending on which term you're using. Remember, our previous calculation was d theta of f was, well, let me just go back and make sure I'm doing it right. It looks like it was, oh, okay, I can just go on the second page. So it looks like minus rs fx plus RC Fy. Okay, so now I'm going to replace f with fx. So dd theta fx is going to be minus rs fxx plus rc fxy. And I'm going to do the same thing. I'm going to replace f with f sub y. So now you just write it again. So minus rs fyx plus rc fyy. Okay? So what I will do is just plug these two expressions into what I want to compute, which is up here. Okay, so now we will have 4 terms to think about. So C is multiplying this bottom box here. So minus rs fxx plus rc fxy. And then we'll have an S term too. And this will look like minus rs fxy. I'm switching fyx equal fxy. Remember, for example, if you have f equals x times y, f sub x equals y, f sub xy equals 1, f sub y equals x, f sub yx equals 1. So these are equal. Now, if I return, I just need one more term, and that is this last term here, just in case you're getting lost. So plus rc f sub yy. So if I just simplify, I want to just collapse these two terms here, the fxy terms. So we have minus r cs fxx. Looks like we have, I'm just going to put that xy here and put parentheses around all the other stuff. So I'm going to factor that r out, and it looks like we have c squared minus s squared. Unfortunately, that's not 1. That's just a thing. It's actually cosine 2 theta, roughly speaking. So then finally, plus r s c f y y. And we can just factor. Remember that RSC, it actually shows up 2 places. So RSC FYY minus FXX. Finally, plus RC squared minus S squared FXY. I'm just rewriting some stuff here. So now we're essentially done, because we already have our second term that we did earlier for the theta stuff. So now we just add. ZR theta, the mixed derivative, is just the non-theta stuff. So RSC FYY minus FXX plus RC squared minus S squared FXY plus the theta stuff. So how about I just put a minus SFX plus CFY. That is it. That is our mixed derivative. There are 3 terms. And you can see it's kind of a challenging calculation. But it turns out that in applications, a lot of stuff will cancel. So it's worth it to do the calculation, because you'll end up with something simpler. You don't need to know this, but just to hint at what you'll end up seeing, if you change this expression, zxx plus zyy, it turns out this will just become zrr plus 1 over r squared z theta theta. And this is nice. Right? It's not nearly as nasty as all this other stuff. And this thing is called the Laplacian, or the gradient squared. But you do not need to know this. But it turns out this will show up basically everywhere in upper division science courses. So these calculations are worth knowing. Okay, that's it. Thanks for watching.